Okay, welcome everybody. Thanks all for coming. I'm Ruth Das from the Social and Public Health Sciences unit. It's nice to see everybody here for the first in-person Morris Block seminar for quite some time, and I think for some people it might even be their first ever in-person Morris Block seminar, so it's great to see you all. Today we've got Jay Kaufman, and he's a professor in the Department of Epidemiology, Biostatistics and Occupational Health at McGill in Canada. He's also visiting professor at schools of public health, a few of them, one in North Carolina, one in Michigan, and one at the University of Chile. And he's a social epidemiologist, and he's got an interest in sort of methods and causal inference. And he works on a whole range of, I would say, like health outcomes. So he's not specific to one health outcome, so we might hear about a range of different topics. And today he's going to talk about the interface between epidemiology and economics and some of the challenges in that space. So thanks very much, Jay.
Thank you. Thank you very much for inviting me. I guess this is also on Zoom, and I can see the Zoom window here, but I see myself. I don't see my slides. So do I need to share the slides?
No, it's recorded by using Zoom. It's not being broadcast anywhere. So.
Okay. So the Zoom recording doesn't see the slides. Is that the way it's supposed to be?
Yeah, that's the question I do not know the answer to.
Okay.
No, it's fine, because I think, yeah, you're sharing your screen, so it should be okay.
Oh, okay. Very good. All right, great. Okay, well, thank you, and here we go. I guess we have about an hour to talk about this this question. I tried to think of a talk. I didn't want to bring the usual kind of research talk, like here was a data set, and I ran this regression, and I got this result, and it has 3 stars next to the coefficient. Like, I wanted to talk about something a little bit broader, more philosophical, more interdisciplinary, digging a bit deeper about academic culture and so forth. And so I decided to talk about this question of quasi-experimental methods and the relationship between epidemiology and economics in the borrowing of those techniques. So I guess it's in this institute, it's becoming very common now for people to use these kinds of natural experiments, quasi-experimental techniques, mostly borrowed from econometrics. And it's typical now of a lot of social determinants of health research in public health generally. So we see a big increase in the publication of papers that use these kinds of terms, use these kinds of models. And so it's interesting to think about the cultural aspects of that, and in terms of borrowing a set of methods and a set of priorities that go along with those methods from one discipline and bring them into another discipline that has a different history and a different foundational philosophy. So it leads one to think about the ramifications of that cultural borrowing. It happens anytime 2 cultures come into conflict, like under colonial conditions or other kind of historical conditions. When 2 cultures collide, there's a kind of a syncretism and a synergism between them, and some borrowing and some assessment of different priorities. And so we can do this for epidemiology and economics as well, because they have very different foundations and assumptions. So in the first 12 slides or so, I'll touch on a set of issues around those different perspectives on causal inference and identifying causal effects between the 2 different fields. And obviously I'm coming from one of the fields, from epidemiology, and I'm not trying to denigrate another field. I really feel like there are some advantages in the one perspective and some advantages in the other. And so I don't want, if there are economists in the audience, I don't want you to feel like it's a hostile treatment of the field. I admire many of the aspects of economics, and I think it's a healthy thing that's coming into epidemiology, but there are some differences. So it's interesting, actually, we came from epidemiology as this foundational moment with John Snow, and that was a natural experiment. But we really moved very much then into clinical trials, especially around World War II and after that period, focusing the evidence pyramid on the clinical trial, which didn't happen in economics. Starting to happen a little bit with like Esther Duflo and that group, and the idea of clinical trial or randomized trials for policy evaluation. They got the Nobel Prize in economics 2 or 3 years ago about this idea. but still is the case that there's much less of a formal attachment or randomization in economics than there is in epidemiology. It's much more through these kinds of natural experiments and other designs that try to take advantage of exogenous variation. There's some other interesting aspects of the two fields. I guess I don't have a pointer. Yeah, so let's see. Yeah, so there's a tension in epidemiology between risk factor individualism and social determinants of health. Risk factor individualism, like, well, you know, people get sick because they smoke, and so we have to get them to not smoke so much, and that's, you know, they have some personal agency there, and we have to, as public health people, we have to get them to not smoke. Versus a kind of a social determinants approach, which says there are structural things in the society that lead some people to cope by smoking, and so we have to change these structural things. And you can see a kind of a parallel tension in the history of economics between the idea of rational individualism, that people are agents trying to maximize their utility in society, and the countervailing force of political economy. I mean, most notably from Marx, saying, no, there are structural factors, historical factors that guide the development of different kinds of economies that have different kinds of structures, and that's what constrains people's lives. So you see this mirrored in the two fields. Another interesting aspect is that if you look in any epi textbook, all the equations use capital sigma, because epidemiologists think that inherently everything is categorical. Like, you're dead or you're alive, and that's a binary decision, so it's a logistic model, and so we adjust things by summing over these categories. In economics, they love the linear model, they love continuous outcomes, they love the normal distribution, they love the mean, and so everything is viewed as a continuous variable, which, if modeled as a categorical variable, is just a mismeasured version of the continuous variable. So they say, wow, it's not really that you're dead or you're alive. You know, we have qualies and dallies, and people are 80% alive or 20% alive, and so they model things that way. So I'm serious about this, that it really is a philosophical difference between whether the world is ultimately continuous or whether the world is ultimately categorical. And that has implications for the kind of models, you know. And with a binary outcome, the epidemiologist always run a logistic, and with the economist always run a probit. But of course, the probit is based on the normal distribution, normal continuous distribution, and cut points in that normal distribution. So it does have these implications for practice. When we get to the issue of causal identification, there really is a big cultural difference between the fields, because the epidemiologist's general approach, traditionally, is to say, well, there could be some covariates Z here that confound the causal effect of X on Y, and so we'll just adjust for those. So we'll measure them all, we'll adjust for them all, and then we'll get the causal effect. An economist would never buy that story. You always have to come up with some identification strategy in the design or the analysis that would allow you to identify that causal effect without having to assume that you were able to think of all the Zs and measure them all and adjust for them all. That they would view that as just an impossibility. Like, it's just absurd to think that, you know, with something as complex as human behavior, that you would know all the Zs and just measure them and adjust for them. So they always need some kind of a motivating identification story for how it is that the variation that you intend to model is exogenous to the exposure, and that the causal effect is therefore identified. So once you have that story, then you have some kind of an estimation procedure that gets the causal effect by looking at the expected value of the outcome if you were exposed versus unexposed, in the same way that epidemiologists do. But you can't publish without that identification story. And that's something that's lacking in epidemiology. I mean, here's a place where I think economics is ahead of the game in prioritizing that identification strategy. Well, I guess I've already said the epidemiology approach is based on this idea that you exhaustively adjust, condition on, or standardize for all the Zs. And that allows you to make a model for the unobserved counterfactuals, make a model for the unobserved counterfactuals in relation to the observed things that you have in your data set. So it's this assumption of exhaustive measuring of all the Zs without any measurement error that allows you to make that identification story. The same story that economists would say is dead on arrival. Right? It's never plausible that you would measure all those things. But there are assumptions behind the economic approach as well. So the economists might say, well, there are always going to be some unmeasured things that confound X and Y. You're not going to be able to adjust for those things. And so you're always going to be vulnerable to those things. So what we have to find is some exogenous source of variation, Z, something that affects the exposure, but doesn't have any connection to the outcome except through the exposure. And if we find this exogenous variable, then we can say that we can identify the causal effect. This is the famous instrumental variable formula that underlies so much of identification strategy in economics, and also in some epi techniques like Mendelian randomization. But you see that this is just shifting the impossible story from one variable to another. Because while they were incredulous that there would ever be an X that wasn't confounded by some U, they are willing to believe that there's a Z that's not confounded by some U. So you are telling the same story about a variable that has no unmeasured common causes with the outcome. It's just no longer your exposure. Now it's something else. And that sounds like, well, you're just, moving the impossible step from one place to another. But the economists will say, well, there is an advantage to this because I can look for a Z. I only have one exposure, right? I'm stuck with the exposure that I'm interested in, which is, the thing I want the causal effect for. But I can search around, and among all the possible causes of that exposure, I might be able to find one thesis condition. So it gives me some more degrees of freedom, say, to find this thing. But still, ultimately, if you don't believe that a variable is unconfounded, you shouldn't believe that for the Z any more than you do for the X. Now, the other thing that economists are much more focused on is this confounding, but there are other threats to causal validity that get much less attention in economics and more attention in epidemiology. One is selection bias, which is conditioning in some way on an effect of the exposure and the outcome, a common effect of the exposure and the outcome. We also call this collider stratification bias. There are some other forms of selection bias that don't necessarily involve collider bias that have to do with effect measure modifications. It's a little bit more complicated than that. But in general, this gets much less skepticism or attention in this identification story by economists. And measurement error is another one where there's some attention to measurement error, but not nearly as much as for confounding. So there's a little bit of prioritization there in that field for the big danger and a little bit of neglect for the others. Another issue that comes up in the difference in approaches between these fields, and it has a little bit to do with what I talked about before about continuous versus discrete. Because if you're discrete in your outcome, then you're generally going to fit some kind of a nonlinear model, right? So you're going to fit logistic regression or a Cox model or something like that. And these are generally ratio measures of effect. So you find the ratio measure of effect much more common in epidemiology. Economists, as I said, love the normal distribution, the linear model, and absolute effect. And so they're much more likely to fit those kinds of models. So everything is done with OLS if possible, and that gives you additive scale effects. And there's no natural priority to effect scales. Like effects exist at every scale, and there's no particular reason why you would believe one scale or another. Like, for example, if I say that the effect of risk factor 1 is to give you an extra 5 units, and the effect of risk factor 2 is to give you an extra 10 units. What is the effect of having both risk factors? Well, the answer to that question, there's no objective answer to that question. It has to do with whether you're an economist or an epidemiologist, whether you think it's the sum of those two numbers or the product of those two numbers. It's a completely arbitrary decision based on which model you happen to like. And the joint effects between those risk factors, of course, can fall on any scale. It can be additive or multiplicative or more than additive or less than additive or more than multiplicative. They can be anywhere along there. And this becomes very consequential in a model that's very common now in economics and becoming more common in public health, which is the difference in differences, which achieves this identification story, the story about how is it that you identify the causal effect. It achieves it through extrapolation of a model, of a parametric model. So you fit this straight line through your data, and then you fit an imaginary line that keeps going by extrapolating that straight line. You just follow along that straight line, and then when the data stops, you just keep going. And that's your counterfactual that you didn't observe. And you follow a straight line that's straight on one particular scale. So which scale should it be? Well, that's this arbitrary cultural decision. So if you take the simplest case, the 2x2 case here, where you just have, like the two-way fixed effects kind of standard difference in differences model, I'm going to model this 2x2 table with intercept, the time effect, a group effect, and an interaction term. And I'm going to say that interaction term is my causal effect, because that's my deviation from the expected value under the null. But what value for that interaction term represents the null? say my time effect is 5 and my group effect is 5. If I see 10, would I say, well, that's the null? Or if I see 50, or 25, would I say that's the null? There's no unambiguous answer to that question. If I'm an economist, anything that's different from 10, I've discovered a causal effect. If I'm an epidemiologist, anything is different from 25 is considered a causal effect. And so that, and this has to do this has consequences also for the assumption for diffs and diffs of the parallel trends before the intervention, that those are parallel on one scale or the other. This is the kind of consequential thing that doesn't get talked about enough. Now, another thing, I'm just skipping through a bunch of these issues, and then I'll get to my case study in a moment. Another huge difference, as you know, is estimation versus testing. Economists are still strangely hung up in the world of p less than 0.05 as evidence of something that's true, and the use of significant stars and crazy things like that. I don't know how things are in your institute here, so I don't want to be too disparaging, but epidemiology has largely moved beyond that due to the very active agitation by people like Ken Rothman and Sandra Greenland and other very strong anti-testing people. We've moved in epidemiology much more toward estimation of point estimates and interval estimates as representations of uncertainty, and not this silly, oh, I got 0.049 instead of 0.051, so I've discovered something. Like that obviously doesn't hold, but in economics, they're not quite there yet. Now, there are some critiques within economics of this as well. Deirdre McCloskey has a great book about this, and some other economists have said, okay, we know that this is kind of silly, but in general, the field still continues in the same way. Then, of course, there are maybe more superficial aspects of the different culture, between the two fields. Talked about presentation and publication style, things like significant stars. You notice that economics papers are 50 pages long, whereas epidemiology papers are only 3 pages long. So economics papers are much more exhaustive in pursuing different sensitivity analyses and specification tests and things like that, whereas epi papers, you only get 3,000 words, so you barely have time to present one model. If you're lucky, there's an appendix where you can put some other things that nobody reads. There's sort of stereotypes about pathological levels of self-esteem within the economics field. And I guess we have a few of those people in epidemiology as well. The issues of non-cognitive skills like impulse control. I can tell that there are no economists in the audience, because if there were, you would have stopped me 4 times already to raise questions about things. Because economists are not able to just sit and listen to a talk. They have to, so there's a joke that like when you give an economics talk, you only need to bring 2 or 3 slides because that's as far as you're going to get. So I know when I'm speaking to a public health audience because I'm getting through my slides. And then, there's just general dress and presentation. You can tell a very nicely dressed $1,000 suit, Raj Chetty there from Harvard, compared to, some epidemiologist that wandered into your seminar. Looks like a crazed person. So, it's pretty easy to tell who comes from one tribe or the other. Another interesting difference is, I don't know how things are in your institute, but at McGill and in many other schools of public health in North America, it's almost all women now. We have an older cohort of full professors that are largely old men. But among the new recruits coming in, getting their PhDs, becoming assistant professors, it's 70% female. And that's a transition that has not yet happened with economics. So that's another interesting aspect of the cultural difference. I don't know what the reasons for that are, but it's interesting to observe such a dramatic difference between the gender distribution of the fields. All right, so let me go to my case study here. So that took about 20 minutes, and let me spend the next half an hour or so on one cultural difference, which is how we handle clustering, right? How we think about multi-level models. Diffs and diffs is a multi-level model because you have units that are measured at multiple times, comparing before and after. So you have to treat it as a multi-level model. And we have, in epidemiology, we have longitudinal studies, very common. In economics, I have panel studies that are very common. So we often have to treat this kind of clustering. And the question of how we treat that reveals something about our cultural assumptions and our cultural priorities and our preferences. So I'll take a worked example here, a very good paper. And again, I want to make it clear that I'm not picking this paper to ridicule it or criticize it in any way. It's actually written by economists, British economists. I know Alice Goisis is in London, I guess at UCL, I think, a demographer there. The senior author is, I think, a demographer from Finland who's now at the Max Planck Institute. So these are all good authors, a good paper and a good journal. And I'm going to maybe, it seems like I'm criticizing the approach. I'm going to show some weaknesses of the approach. But I think, it's a strong paper and they do what they want to do and they do it very effectively. So I'm not criticizing in that sense, but it does reflect the way that priorities can kind of get in the way of learning about your problem. So that's why I'll use that. It has to do with the evaluation of technologies for assisted reproduction, right? So this is about the safety of IVF and other related techniques for getting people pregnant, which are very common now in the rich world. And obviously people have some questions about whether they have any adverse effects. And so it's quite appropriate for the Lancet to publish a paper about this kind of thing. And of course, it's very difficult to study because there's a reason why you use assisted reproductive technology, because you have some kind of subfertility. And so it's not randomly distributed in the population. And that's like what we call confounding by indication, which is very hard to get rid of. It's hard to find people using this technology who don't need it, right? So this is a real challenge. And so they very cleverly use clustered data, matched data, in order to try to remove this kind of bias using a very popular technique, which is sibling fixed effects. So in a multi-level model, you can do it as random effects or fixed effects, of course. And the sibling fixed effects are matched pairs of siblings where they're selected to be discordant. So one pregnancy was achieved with reproductive technology, the other was not. And now we can compare the two outcomes. And because they're matched within a family, this eliminates all the confounding by things that are shared within the family. So socioeconomic status and diet and genes and all the things that you could never possibly measure. So that's why it counts as a quasi-experimental design, because it has a strategy for getting rid of all those those unmeasured variables that you could not possibly measure. We don't know all the genes that make people subfertile and that might affect their outcomes. So there's no possible way that we can measure these things, or the diets or the stressors or the community green space and all these other unimaginable the dimensionality of things that could affect it. But they're all controlled in a design that takes one sibling versus another sibling in the same environment with the same parents. So this is a good study then that got a lot of attention and reassuring attention. So all the headlines came out and they said, the study showed that these technologies are just fine. No problem. It's all null here, nothing to see, move along. So lots of, in all different countries around the world, lots of press attention. Of course, Lancet is a very high profile publication, so it gets a lot of press with that reassuring message. Okay, so this comes from Finnish population registers. They have this advantage, of course, of having the entire population in their data set. They have this register of 20% random sample of households that have more than one child, age 0 to 14 at the end of 2000, and they select a set of birth cohorts there, 1995 to 2000, and they are able, because they have all the data on these people, it's Finland, of course, so they are able to identify the use of assisted reproductive therapy through the prescription drugs that the mom took, because prescription drugs are part of the medical record. There are certain drugs that are typical of people involved in these procedures, and they're able to track the use of those drugs and identify that this was a woman using one of these 4 ART techniques, IVF, artificial insemination, ICSI, which is actually taking the sperm or a piece of the sperm and actually shoving it into the egg, and with fresh or frozen embryos. So some restrictions here, certain age range, no triplets, and they look at 4 birth outcomes here, 2 continuous and 2 categorical. The categorical are just categorical versions of the 2 continuous things. You take birth weight, or you have birth weight with a cutoff for low birth weight. You have gestational age or a cutoff for premature. They have some measure covariates here at the child level or at the mom level. So a pretty rich data set of socioeconomic and other variables that they can adjust for. And they're very smart about not adjusting for mediators, very clever. So, it's a strong paper in all these senses. And then they take 2 modeling approaches. So this is one reason why I picked it as an example, because it's a very good exercise in being able to compare the 2 ways of doing things, the epi way and the economic way. They're demographers, so I guess they stand in between those traditions, and you can make the side-by-side comparison. So the standard approach, of course, is to take all these variables they have and measure them and adjust for them. And the alternative approach is this fixed effect, sibling fixed effect model, where you're going to take a kid who got ART and a a sibling who didn't get ART and only compare those. So those are the two approaches they're going to take. And as I mentioned, this advantage of the sibling fixed effects is that it gets rid of all the unobserved confounding that's shared between the two. Now, it would not get rid of unobserved confounding that's not shared. In a typical diffs and diffs, we say, you know, like the fixed effects get rid of all the time invariant variables, but things that change over time, like that might be different before and after the intervention, those things remain as potential confounders. And that's true here as well, except it's not across time, it's across siblings. So, you know, if income changes, you know, I have my first kid and then somebody in the household loses their job, and then the second kid is born with a lower income, then they're not exactly matched on those things. So you have some difference, and they adjusted for the variables that they had for those things. And there were a couple where they didn't bother adjusting because there wasn't any, so there could have been change theoretically, but in practice, they didn't observe any big change. Okay, so for the continuous outcomes, they ran linear models, and for the categorical outcomes, they ran actually linear models. So they did like economists did. Instead of logistic regressions, they kept everything on the linear scale here. So they ran linear probability models. That's another thing that epidemiologists would never do. It's a perfectly legitimate thing to do, but epidemiologists are so hung up, biostatisticians as well, so hung up about the violation of homoscedasticity in these models that they'll never run these. But economists do it all the time. And I think it's perfectly legitimate, but it's not part of the epi tradition, so we don't do it. But this is nice because it keeps everything on the same scale. So you get everything on the absolute scale, and it's easier to make comparisons. Fitting a bunch of models then with increasing control for covariates. And the authors mentioned, well, look, this is not the first study that's done this, but the other studies who did this ran random effects models for the clustering. And so that's no good. So we're going to contribute to the literature by running this fixed effect model. And this is to improve upon the fact that the previous papers used this random effects model that could mislead you. So that raises an aside on what's wrong with the random effects model, because this is another big cultural difference between economists and epidemiologists. That epidemiologists and biostatisticians fit random effects models all the time without feeling any need to justify that in terms of some assumption. It's just, oh, I woke up and it's a Tuesday, so I think I'll fit a random effects model. Like in the literature, you see it represented that way. Whereas economists will never fit this model unless they go through a series of checks to make sure that it's not broken. And that's a really interesting difference, which I don't have any understanding of why we had that difference. Like, why are epidemiologists not concerned with the violations of that model, potential violations, to check those things? I don't know, but they're not. So I've asked about this and I've not really gotten a good answer from anybody. I think it just shows the power of cultural norms to say, like, this is in our toolkit and we're just going to use it, as opposed to economists who are taught to treat this very, very skeptically. So I need to go on an aside for 5 or 6 slides and say, what's wrong with the random effects model? So let me, I don't have the GOISIS data, so I can't analyze that. So I'll grab another data set here of birth outcomes. And let me ask a question about smoking. I have smoking in this data set here. And what's the effect? I have pregnancies nested within mothers here. So I have multi-level data. And I can ask the question, what's the causal effect of smoking? So I could just fit that in a regression model. But of course, the standard regression model would be wrong, right? I might have covariates at the kid level, covariates at the mom level, but this error term here is misspecified because I have this clustering. They're not independent error terms because kids within the same mom are more correlated. So this model is not valid. I need to go to a multi-level model, and I'll specify here a random effects model so that I have a variance term for the mom and a variance term for the kid. And I say that these variance terms are deviations from the mean in that group. You know, like each kid is the deviation from the mom's mean. And so I have the mom's intercept as a normal variable and the kid's deviation from their mom's mean as a normal variable. This is a standard multi-level linear model. So this is my random effects model. And when I run that, I see that smoking costs you about 200 grams. I've adjusted for all these other covariates that I have available, and the moms who smoked lost about 200 grams in pregnancy. Okay, so that looks fine. And if I were an epidemiologist, I'd just go ahead and report that. Smoking costs you 200 grams. But if I were skeptical and I wanted to investigate this further, I might try a couple different ways. So the first thing I can do is to fit the ecological model. Suppose I only had ecological data, the data at the higher level. For all the moms, I have the average birth weight for all their kids, right? So I have smoking moms and non-smoking moms, and I can look at the average birth weight of smoking moms and non-smoking moms and compare them. And we typically have data like this. We might have a community mean. We have census data with a mean for a community, and we look at characteristics of rich communities versus poor communities. So we often fit models like this, but we should get the same answer, right? The average birth weight loss for smoking moms should be 200 grams less than the average birth weight loss for the non-smoking moms. So I can fit this easily. I'm showing Stata code here, by the way. I don't know what software you use, but I happen to use Stata. So there's a handy command in Stata that does this between model here for the ecological model. And I see something surprising, which is that smoking at the ecological level will cost you 300 grams, not 200. So that's the first sign that something is broken here. Then I can go the other direction, and I can say, what is the effect of smoking within the same mom, right? I have two kids of the same mom, or two or more, and she smoked in some pregnancies and she didn't smoke in other pregnancies, and I'm only going to look at the variation within a mom. This is, in fact, the equivalent of that sibling fixed effect model. This is a fixed effect model, and I'm looking at two siblings from the same mom, so essentially doing the same thing. So now I can't have any confounding between mothers. I'm only looking within a mother. I'm controlling for all the unmeasured aspects of the mom, her genes, her diet, and so forth, looking at two siblings. And now I see that smoking costs you 100 grams. So I got three answers now: 100 for the fixed effect, 200 for the random effects, 300 for the ecologic model. The fact that those are different is a function of the fact that the random effects model is broken because the random effect is confounded with the exposure, right? It's very clear that the moms who smoke have some unmeasured characteristic that is different from the moms who don't smoke. Maybe I don't have alcohol consumption here, I don't have diet, I don't have physical activity. There are a lot of things that could be different between people who smoke during pregnancy and people who don't. And something is confounded here. So this model is broken. It's just no good. You can't use the random effects model here. So economists would make a test for the difference between these. They call this the Hausmann specification test. It's easy to fit in Stata. You just put the two models in and say Hausmann, and it gives you the test for the difference between the coefficients under the fixed effect model and the random effect model. And if they're significantly different, the economists throw away the random effect model and say it's broken. I don't know why epidemiologists don't do that. I guess we don't believe in tests, so we can't really do this as a test. But at very least, you could look at, see 100 is different from 200 and conclude that this model might not be the best way to find out what's going on. So this is their critique of the random effects model. And I think it's a valid critique that epidemiologists need to pay more attention to. The random effects models can be broken by this confounding between the random effect and the exposure. Okay, back to the Lancet paper. They had 65,000 kids here, and they found 2776, 4% were conceived by ART in the relevant time period. About 1,200 of those were available for sibling fixed effects analysis, and 578 mothers. So off they go with this small sample of about 1,000 kids out of the original 65,000. And here's their main results. Just going to the sort of the final model here, you see that in the Epi approach, you lost about 60 grams there for of birth weight, and you had higher risk of, you lost 2 days of gestational age and higher risk of low birth weight and preterm birth. But when you do the sibling fixed effects, all of those are only about half as big. You only lose about 30 grams instead of 60. You only, instead of losing 2 days, you just lose a little bit more than a day. And your risks of low birth weight and preterm birth are much more modest. So these confidence intervals include the null, and so they conclude nothing going on here, nothing to see. The epi analysis would scare you and make you think that something bad is happening here. But when we do the proper adjusted analysis, adjusting for all these unmeasured confounders, we get rid of all that confounding and we get the pure causal effect, and there's nothing to worry about. Go ahead and have as much ART as you like. So that's the way they do it. Now, I've over the years written a bunch of commentaries about some dangers that I saw in these kinds of approaches, so I'll mention some of these concerns now. First one has to do with selection bias, which, as I said, economists are not as tuned into as epidemiologists, not as focused on this. But, you know, I picked 1,000 kids out of 65,000. That's only 1 out of every 65 kids got into my sample, right? And it's not a random sample. It's a very particular sample that's fit with a particular requirement, which is that X1 has to be different from X2. And that's a very distorting restriction. And the reason it's a very distorting restriction is that because by the natural order, and this DAG, by the way, is from a paper about 10 years ago from a group at Sweden, Karolinska. First author is Frizzell here. And there's the paper. Under this natural order here with the shared confounding, kids are naturally going to have the same ART. Why is that? Because if you have a subfertile mom, she's going to be subfertile all the time. Like if there's something in her environment or in her biology that leads her to have difficulty getting pregnant, in most cases, that's going to be consistent over time. And so the vast majority of kids either never need ART or always need ART. And it's relatively rare that you have the situation where one is different from the other. And this would be true for smoking and many other things that we do sibling fixed effects for. So you're sort of violating the natural order here by restricting to those rare cases where they're different. And when you do that, you have this other pathway here that goes from the subfertility and the other common causes of the exposure and the confounder of the first kid's exposure, C, that shouldn't have anything to do with the second kid's exposure, right? There should be unique elements of confounding. You know, one kid was born in cold weather and the other kid was born in warm weather, or some, some random thing like this that affects their outcome, or an infection during pregnancy, or some other kind of random thing. There should be sources of exposure and outcome that are unique to the kids. But because of this collider, we call this a collider at X1, because the shared causes of the exposure feed into X1, and the confounders, the other causes, the non-shared causes also feed into X1. And so when we condition on X1, we create a correlation between the parents of X1. So now FX and C1 became correlated, and that makes X2 as a child of FX correlated. And so now we've introduced a new confounding that didn't exist before. So this is the danger of the selection bias, is that we've upweighted idiosyncratic cases. You have to think about why it is that one kid gets ART and the other doesn't. It's because something idiosyncratic happened like that. And these might be rare in the population, but common in your study sample because of the way you required people to enter into it. So because the exposure is influenced by familial factors, unshared confounding will be increased by this restriction. So you have a trade-off here. You've gotten rid of one kind of confounding and you've introduced another kind of confounding. And surely both kinds of confounding exist. And so the question of whether you're better off at the end of the day or worse off at the end of the day by this procedure is a question of which source of confounding is larger. And you're not going to know that. You know, these arrows in this DAG don't have any coefficients on them. I don't know which is larger here and which is smaller. You might have some subject matter knowledge about which is larger and which is smaller. And in fact, in some related articles by Frizzell and Scholander and some other folks, they do speculate that the advantage might outweigh the disadvantage here, but it's completely speculative, right? Because of course you don't know all these confounders, they're unmeasured. If you had measured all these things, you would have just adjusted for them. So the whole point is that they're unmeasured. And so it's difficult to speculate about the things that you don't know about, right? It's like Donald Rumsfeld's known unknowns and unknown unknowns. You have a real problem here weighing between the trade-off between the unknown unknowns. Another implication has to do with measurement error. And that's the fact that some kids, you know, this procedure that we have for identifying ART based on prescription drugs, it's a good algorithm, it's been validated, but it doesn't have 100% sensitivity and specificity. So there are some kids who are getting ART who are not captured by this algorithm because the prescription isn't registered for some reason, or there's a mistake in the registry, or because they're a rare person who's not getting that particular drug or whatever. And some people getting these drugs for some other off-label indication or some administrative error. For whatever reason, the sensitivity and specificity are not perfect here. So one explanation for why the ART exposures differ between the two kids is that one of them is a mistake. Now that could be very rare in the population. If the sensitivity of this algorithm is 98% or 99%, then only 1 per 100 will be affected by this misclassification, and that's trivial. in the big data set, in the whole data set. But in your selected data set, you've upweighted all those mismeasured ones because you need discordant kids. And so for whatever reason they become discordant, they get prioritized to enter into your data set. And this means you have added more measurement error in your sample than existed in the population. Now, if this is random with respect to the exposure or the outcome, which it may be, if it's an administrative error, it might be random, then it's just going to bias you toward the null, right? So this just maybe reduces your power to detect something, introduces some reduction in your effect magnitude because of this upweighting of random error. So among discordant siblings, fewer will be correctly classified on exposure than in the population, leading to attenuation of observed exposure associations. Attenuation under the assumption that it's non-differential. Now, Terry Keyes and co-authors commented on this and said that they thought that it was likely to be differential. First of all, they noted, by the way, I didn't know this, but they noted that this measurement error problem had been previously identified by an economist. Okay, so I have to give econ credit here. John Bound, a great economist at the University of Michigan, pointed this out in 1999, that this measurement error gets inflated in the selected sample. But they also noted that it's likely to be differential. And they give the example of smoking. If the mom smokes in the first pregnancy and the kid has a birth defect, the mom may well quit smoking and not smoke in the second pregnancy. And so even under the null, that smoking has no effect on birth defects, you'll see this association between smoking and birth defects because of this this pattern that the exposure is more likely in the first pregnancy than in the second pregnancy. It's basically confounded by birth order, right? Their argument is that there are women who will smoke in the first pregnancy and something bad happens, so they quit. But there are very few instances of someone starting to smoke in the second pregnancy. So if you get a misclassification where it's the second kid was smoking and not the first kid smoking, it's more likely to be an error than the first kid smoking. So they're making this argument that when you think of it in substantive terms, this is not non-differential misclassification, it's differential, which means that it could be larger in magnitude than Frizzell points out, and could be in any direction, not necessarily toward the null. Could be, it's unpredictable which way the bias is going to go. Scholander, in a later article, it's part of the same group at Karolinska, also pointed out that you have to make an assumption of no carryover effects. It's also possible that a bad outcome in the first pregnancy leads you not to have another kid, right? And that selects you out of the sample because you need to have at least 2 kids to get into the analysis. So if I had a birth defect or some adverse outcome in the first pregnancy and I said, well, I'm having enough trouble with this child, I'm not going to take my chances and have another child now, that selection out of the sample by only having 1 kid would be differential with respect to the outcome and would contribute to another kind of bias. That's a kind of a carryover bias. That is your exposure, well, your selection into the study. I mean, Keyes mentioned before that your exposure could be affected by the previous outcome. Here he's saying your inclusion in the study could be affected by your previous outcome. So that's an even more severe critique. Now, I'll take another entirely different critique. So leaving behind that DAG of selection bias, go to the issue of statistical power, right? Because you have to be able to detect this effect. Let's take the simple example of 100 matched pairs. So 100 kids with ART, 100 kids without ART. If you think of those in 2x2 tables, there's only 4 ways that can work out, right? We have a cohort study here, so the exposed and the unexposed can both get the outcome, or just one of the 2 can get the outcome, or nobody can get the outcome. And those are the only 4 ways it can work out. So if you want the effect, you just take the Mantel-Hensel over all of those pairs. You just need to know the number of each of those pairs, the TUVW pairs. You just need to know the number of each of those pairs, and you can do the analysis that way. And you can see who's contributing here to the numerator and the denominator of this Mantel-Hensel, right? That the T and U pairs add to the numerator, V and W pairs add nothing to the numerator. The T and V pairs add to the denominator, and the U and W add nothing to the denominator. And then you sum these all up to get the chi-square. So you see that the W pairs are completely uninformative. They don't enter into the value of the effect estimate in any way. You can have 1 million W pairs and your effect estimate is not going to change, nor is your precision, right? They're completely thrown away, right? In fact, your risk ratio is just T plus U over 2 divided by T plus V over 2, right? The 2's cancel out, so it's just TU over TV. There's no W's there. The W's are completely irrelevant. Now, who are the W's here? The W's are all the kids. Take a categorical outcome like preterm or low birth weight. It's all the people who don't have low birth weight, right? Who didn't use ART and don't have, well, used or didn't use ART, but didn't have low birth weight either way. Well, that's almost everybody, right? The prevalence of these outcomes is about 7%, 5%, 7%, something like that. So 93% of the data is completely thrown away by the fixed effects here. So you thought you had 1,200 people in this study, but really you only have about, I don't know, 10 or 15% of that, right? You're throwing away almost all the data you have. You're doing this analysis of 65,000 kids on 100 to 200 kids, right? When you think about the fact that most of the data are completely irrelevant to the effect estimate you're getting here. So I commented previously that this can be a situation like chemotherapy where the cure might be worse than the disease, where you might get killed by the treatment before it cures you. Thinking of this, ridding yourself of all this confounding by essentially ridding yourself of all the data, right? Going from 65,000 to about 100, you're getting rid of 99% of the data, something like that. And yes, you may have, you know, a data set that meets your criteria now, but it might be so highly selected and so small in terms of power that you're not going to detect anything, right? Bias is not your only source of error here. And this is where, again, I think is a cultural difference where economists are so focused on the identification strategy for confounding that they're willing to do almost anything to rid that data set of bias. And so that story about I got rid of this and I got rid of that and I got rid of this other thing, and now I have this valid subset where I can get the causal effect without any of this polluting bias, that's very strong for them culturally. But, you know, you have to think about your statistical test. They're economists, so they're doing a statistical test. Your power to detect something gets smaller and smaller and smaller as you start removing all these people. And that's even aside from the issue of selection bias, that you're getting a sample that doesn't look anything like the population. So, you know, the bias variance trade-off that was discovered by the empirical Bayes people in the 1950s, you know, Robbins and who's the other guy, Charlie Stein, right? You know, they figured out, and this is the foundation of random effects models too. Random effect models are biased. We know that they're biased, but they're biased in a way that reduces your variance more than the bias that they add. And so, you know, on average, you're doing better with the random effects. That's if it's not broken by this confounding. Under the ideal circumstance, they're biased because they're shrunk toward the mean, but that shrinkage is good because it gets rid of some of this variance. So you make this calculated variance bias trade-off in a random effects model to do better. And there's a whole bunch of models that do that, you know, ridge regression and empirical Bayes regression and, you know, all kinds of models take advantage of an estimator that might be a little bit more biased, but has much lower variance. And so you do better in the long run, you're closer to the truth. But of course, here we're doing exactly the opposite. We're taking an estimator that is less biased, but hugely more variable. And that gives us much wider confidence intervals, much lower power to test against the null. And the fact that it's not confounded anymore is the least of our problems, right? Because now we've taken on all these other problems of selection bias and precision. So in that 2008 article I wrote on this Gilman paper, in the full cohort, they got about 1.6. In their sibling fixed effect, they got about 1.2. And the standard error on that 1.6 is about 0.0 or about 0.1. And the standard error on the fixed effect analysis is 0.225. So it's 2.5 times larger, the standard error. All right, so you're going to plug that into the confidence interval, you're going to have a much wider confidence interval. If you visualize that, you can see that if you had a choice, like you only get to do your study once, you know, we're being frequentist here. So we're saying like, this is the distribution of study estimates we get if we did this study over and over again. But if you're doing your PhD thesis or something, you probably only want to do that once. Like just, you know, going through that for 5 years is enough, and no one wants to do that 1,000 times. So you're just going to take one estimate, and you have your choice. You can take it from the unbiased estimator, here, the sibling fixed effects, that's very wide, or you can take it from this biased estimator that's very narrow. And it's a little bit off from the truth, but your expected deviation from the truth is actually smaller than that bias estimator, because there's so many far out values in the fixed effect analysis because it's so much wider. So you're taking a big gamble by drawing from the unbiased distribution instead of the biased one, right? So just for example, if the true risk ratio is 1.5 here, right, you're almost sure to cover that in the biased analysis, but you can pick a lot of numbers from the unbiased analysis that are very, very far away from that. So yeah, it depends on where the truth is. Of course, we knew where the truth was, and we wouldn't be in this game. We already know what the truth is. But you know, if the truth is below the null here, then the unbiased estimator is going to be better for you. But if the truth is anywhere above the null, the biased estimator is actually going to perform better. You're going to get something close to the right value and with a narrower confidence interval. And when you think about that reassuring message from the Go-ISIS paper, right? They say, oh yeah, it's fine. You know, the biased analysis told you lost 60 grams, but we only get 30, which is not significantly different from 0. So we interpret that as 0. So you get 0 effect here because they're testing. So it's combined with the error of statistical testing. It leads people to think that the truth is null, when in fact you have very little information about where the truth is, right? All of the space here that's covered by the biased model is also covered by the unbiased model. When you look at these, compare these likelihoods. So in fact, you don't know anything about where that parameter is. You know very little about where that parameter is. It's only in the testing context that you say, well, because I don't know anything about it, I'm going to decide that it's null. So I don't think that the Go-ISIS paper should be viewed as reassuringly. Now, I'm not saying ART is bad for you. I'm just saying, as a result of this analysis, we don't really know very much about whether it's good for you or bad for you, not much more than we knew before. Okay, so when a very small subset of the cohort is available for the discordant analysis, as in the Lancet paper, one must be concerned about both selection bias and power, and some of those other issues that I talked about with measurement error. You have to think about the story of, you know, how it was that people came to be discordantly exposed, right? There's some kind of story there, like how it was that, you know, I took ART, but my sibling didn't. If you can't really tell that story in a way that makes you think that that's the group of people you really want to study, then you could be in some danger here about the selection bias problem. And then, of course, misclassification and power and stuff make this more complicated. If you take an estimation approach that you want to be as close as possible to the right answer, then you really, in many cases here, you're going to be better off with the biased analysis, like the random effects model, than you would be in the unbiased analysis where you throw away most of the data. It's easy to think that this is more of a severe problem with categorical outcomes than it would be with continuous outcomes, because of course in continuous outcome, everybody's discordant. But there is a recent review by Scholander where he does some simulations and he shows that, in fact, this affects continuous outcomes as well. This loss of data because people are close. I mean, in practice, you always have to sort of make some calipers of where you consider people close enough or far enough away. This is very common. I chose one paper for my example, but you can see this in many papers. I'd take another one here from the literature more recently, looking at something similar here. This is preterm birth with long-term risk of heart failure. And this analysis with the full data set and the sibling fixed effect analysis, you see basically the same pattern, which is that the range of uncertainty is completely covered. The range of uncertainty in the unbiased model completely includes the range of uncertainty in the biased model. So all you're doing with this unbiased model is adding more uncertainty. Your point estimate moves a little bit. The point is all of the data, the range of data that's compatible with the model, includes the same range of data you looked for in the so-called biased analysis. So you really just, the major effect here is increasing the width of your confidence intervals. And in a testing environment, that's really hazardous. These authors and most other authors say, oh, well, P is greater than 0.05, so I'm going to interpret this as null. And that's a huge mistake when your strategy was adding more uncertainty to the model. So it makes it almost a sure thing that you're going to declare that it's null. This sibling fixed effects is a very attractive, like conceptually attractive approach, right? It makes sense. You know, why don't I take two siblings that are discordant and then they're adjusted for everything I didn't measure? So it's very seductive. And you see that in the literature, this is increasing dramatically in representation of the literature. So it's very attractive for us. And I'm not saying it's a bad idea. You just have to apply it with some thought about these different priorities. Like, what are you trying to maximize? What are you trying to minimize? What price are you willing to pay for these trade-offs? You have to think carefully about those choices. And then it may indeed be the smartest choice, but it might not be. And that's the sort of weighing of the different options that I'm trying to get across. So, you know, this is something you might see when your computer crashes, and it says click to fix error, and you can't click the button, and then you're stuck. That's the kind of death by fixing that I was trying to get across. Okay, thank you very much.
Thank you very much. That was great. While everyone's collecting their thoughts, I'm just going to make one observation that I think 4 economists that I know that work in the health economics and health technology department at the Institute of Health and Wellbeing are all women. The 2 economists that I know in the business school at the University of Glasgow are men. So, but that's okay. I'm fairly sure that observation is confounded, but there we go. It's just an observation.
Are the salaries the same between the 2?
I don't know that one. Yeah. Any comments or questions?
Thanks, that was really interesting. Kind of on your last point about you know, looking at potentially the biased sample and sort of being able to narrow your confidence interval and be able to make a conclusion versus, you know, the wider sample, or the wider confidence interval, you're more likely to find them out. But isn't that, I mean, kind of my simplistic way of looking at it is like risk of type 1 error versus risk of type 2 error, right? So if you get the biased sample, you're more likely to be committing like a type 1 error, which for me is, again, simplistically, a bit more dangerous actually than a type 2 error, because with a type 2 error, which, you know, with the kind of unbiased sample with the wider confidence interval, if you're committing that type 2 error and you find them out, well, it might generate new hypotheses and cause you to go and seek more data. Whereas with type 1 error, you're making a nice conclusion, but from a biased sample, and that type 1 error might actually lead to more dangerous conclusions because it might actually lead to policy, or might lead to changes, or might lead to action. Whereas a type 2 error may be less likely to lead to action, maybe lead to inaction, which is a problem, but I kind of feel like in terms of if we're hedging our bets or we're looking at like a risk-benefit scenario, I'd feel safer with the risk of committing a type 2 error than a type 1.
So if you were pregnant, or no, if you were a woman who wanted to get pregnant and you were considering ART, you'd be feeling better about the type 2 error?
Well, finding that it's
not finding a harmful effect when there was really a harmful effect.
Yeah. Okay. Yeah.
So, but I do like your approach there, because I think that that's exactly the kind of trade-off that people need to be thinking about. Like, you do have to, especially in a testing environment, you have to think about, you know, the cost of a type 1 error, the cost of a type 2 error, and which kind of error you'd rather make. And that's a calculation that most epidemiologists are not going through with this kind of analysis. So I do appreciate that comment, and I agree with it. But you can see how easily that falls into the temptation of getting a result that suits the needs of a particular analyst. So if I'm working for industry, for example, and I want to show that this product, you know, this may be a commercial product, this product is perfectly safe, right? Then I really love the type 2 error, right? I want to adjust for as many things and condition on as many things and kick out as many things as possible to make the confidence interval wide enough that I get the null, and then everybody's happy because I get to say this product is perfectly safe. That's right. Yeah. Or if I'm a plaintiff in a damage suit, you know, I'm in a jury trial, I'm suing the manufacturer because it harmed me, then I really want to find the effect. So I have different motivations, and this leads people potentially to make one choice or another about which is more attractive. But you can definitely see this, look at funding statements and look at people working for industry versus not working for industry. And you can see how there is a tendency to adjust and adjust and adjust for things to push you toward the null if you have maybe something to benefit from a type 2 error, which is, there are winners and losers in both kinds of errors. So I totally agree with you that one has to weigh, though, the social costs of those kinds of errors. And if we're going to be in a testing world, I mean, it might be better if we just drop testing altogether, but if we're going to be in a testing world, then we need to make that discussion explicit. What's the cost of being wrong in this way? What's the cost of being wrong in the other way? And I'm going to analyze my data reflecting on those costs. Yeah, so I agree with you.
I was wondering if is there anything that economics can contribute that epidemiology should be paying attention to?
Oh yeah, I really hope that I didn't make it one-sided that way. Like I really do appreciate many of the cultural practices of economics and the innovations. A lot of these tools, diffs and diffs, regression discontinuity, and some other variables, they are from economics. They thought of a lot of useful things. And so these are part of our toolkit. We need to use them wisely, but thank God they came up with all these things, and I'm very happy that they use them. And I actually do appreciate this focus on identification. The Epi approach, which is I measured some variables and I adjusted for these, and so here's the answer. I mean, that's a very weak approach. It's very vulnerable to confounding. So the fact that economists are skeptical of that, I think that skepticism is very useful. And they have longer papers. They publish fewer papers. They work harder on each paper. Papers take longer to review, and when they get published, it's a bigger accomplishment. And those papers include many more sensitivity analysis, specification tests, alternative analyses, ways of probing the robustness of the result. And I think that that's something that epidemiologists should also take from economics. The necessity of those kinds of additional robustness tests and validity checks. That's a cultural value that they have. They're very skeptical, and we need to take some of that skepticism as well.
I'm conscious that we're after 2 o'clock, so if people do need to go, then please go. Are you able to take another few questions if people have them?
Oh, sure, yeah, of course. I've
if anyone has comments,
got nowhere to go. I've come all this way, and I have nothing scheduled afterwards. So by all means, I can talk to anybody afterwards. Sure. Yeah.
I just wanted a quick follow-up on that. So as you said, the identification thing, they kind of finding a way to come up with this is the causal factor, or these are the set of causal factors, involves making a more complicated DAG. Effectively, you have to consider many more individual components in the DAG. Is that what you can agree with that?
Well, I don't know. Like a randomized trial has a good identification story behind it and a very simple DAG. So yeah, it won't always be the case that it's a complicated DAG. But there has to be some kind of story there about why you believe that your variation that you're focusing on is exogenous to the exposure. Yeah. So you have to come up with some convincing story. And some of these are very persuasive. Like the regression discontinuity story is that this randomization comes because you have a continuous variable that's cut at some point with a policy decision. Like I give you antihypertensive medication when your blood pressure goes above 140 systolic. So I take the people with 139 who didn't get the antihypertensive, and I take the 141 who did get the antihypertensive. And that makes a very good comparison of people who are essentially the same, except for some noise, some measurement error, but one got treated and the other didn't get treated. And that's as close as I can get to a randomized trial. And that's a relatively simple DAG. Now I have some assumptions there about the running variable, how it can or cannot be confounded. And I have to make some, I can't take people right at the cut point. I have to take some people a little bit farther away from the cut point. So I have to deal with that. And there are complexities there, but the basic story there is pretty simple. And the DAG is pretty simple.
So that was kind of my question is, in doing that, are there other biases that come in simply from having done it like that?
Sure. Like these methods can fail as well. So that, I think for regression discontinuity, there are a bunch of checks that you make. When you publish the paper, and this is another good thing about economics, like they're not just going to say, oh, we did regression discontinuity, you're good to go. They're going to say, well, show us that it's valid because it meets these 6 conditions. You have to go through and show that it meets them. So I've been involved in regression discontinuities that were broken in ways that we found out through these checks, and that was very, very informative. So I think that's useful. If I have a second, I'll give you that full story, which is we looked at Hpv vaccination in girls in Ontario So when the HPV vaccine started in Ontario with public funding of the HPV vaccine for cervical cancer, we gave it free to all girls in school in Ontario at age 11. So it was basically in one class in school. Did it school-based so that it would be higher uptake of the vaccination. We did school-based. So there's a cutoff, there's an age cutoff to get into 7th grade versus not getting into 7th grade, which is December 31st. So if you're born in December 30th, you know, you're in the, I guess in the 7th grade. And if you were born January 1st, you end up in the 6th grade. And so that cut point there is like a random assignment. You know, you could have been born 2 days earlier or 2 days later. And so you're randomly assigned to get this vaccine or not get this vaccine. And this allowed us a population comparison of the effectiveness of HPV vaccine for some acute outcomes that happen relatively soon, things like warts. And it turned out that that was broken. And the reason it was broken was because it was confounded by sexual behavior in ways that we did not anticipate, but we found out about when we analyzed the data because we made these checks. And that's that if you're the oldest girl in the 7th grade, you get a lot more sexual attention than if you're the youngest girl in the 7th grade. And so, you know, just making it into one grade or the other has a huge difference on your social behavior within the classroom. And so, you know, the age at which people debuted different kinds of sexual behavior was very differential by this cut point. And that messed up this analysis. So we found ways to adjust for that. But the point is that we told a nice story, we believed it, and then it turned out to be false. And we found that it was violated by these checks, which the economists force people to do. And that's a good thing, that you find out that all your assumptions are valid.
Yeah.
Yeah, another question. Thanks. It was highly enjoyable, especially for someone who got trained by economists and hated the fixed effects so much that they pursued the PhD on how they got them.
So you're my intended audience, yeah.
So my question should be more appreciating the subtle difference between what the fixed effect is targeting, namely the difference between an outcome within the same mother, or what a random effect is targeting, the difference between two mothers adjusted by conditional being. So basically saying, well, maybe the one, the fixed effects, or the within effect is the one that is closer to the causal effect we're usually interested in. But based on what you said so far, maybe it makes more sense to drop the idea of having this causal effect and maybe go for something that we know is different. Just acknowledging that it's the causal effect we're interested in, but rather different between two people. Different exposure. Okay, you got the point.
Yeah, I mean, that is a really good question. Like, it has to do with your estimand and your target population, and you know what to think about. Sort of what's the randomized trial you wish you could have done here. But the decision for an individual woman to smoke during pregnancy or take ART or whatever is, you know, what if I do this versus I don't do it? So you might say that naturally, then the within woman effect is really the more natural one to be focused on, because that corresponds to the individual decision that somebody would make to expose themselves or not. But at the population level, you might say the policy of making ART available to women is more naturally, it corresponds to having treated women versus untreated women compared to each other. So you do have to make some decision about what's your target population, what's your trial that you wish you could have done. I mean, I guess if you think that there are no crossover effects, you might want to do your trial as a crossover with the same woman getting treated and untreated for 2 different pregnancies. That might be the more ideal trial. But if you randomized women to get it or not get it, and you thought that they were exchangeable, then you might feel that you get essentially the same thing from the randomized trial with different women, but you have to believe that exchangeability assumption that there are no covariates that are imbalanced across those 2 groups. The effect, if there's no crossover, you know, contamination from one pregnancy to the other, the effect on different pregnancies within the same mom should be the same as the effect of 2 pregnancies and 2 distinct women, I would imagine. If there's a biological effect of the exposure, shouldn't matter whether it's in the same woman or 2 different women. So I think that those 2 should correspond. If there are no biases, I think that those should correspond.
So going forward, we should always estimate both effects and be very precise about what we're estimating and how we think the truth is between. So maybe the plot will show at the end the effects.
Yeah, I mean, you know, like I say, under the ideal situation, they're supposed to get the same thing. They're both conditional, they're cluster conditional, they're both oriented around the causal effect of exposing versus not exposing. So you know, ideally you should see the same thing, and there's a certain kind of triangulation then of confirming that you see the same thing with different tools. If that goes well, that you see the same thing, then it's very reassuring. If you see different things, one possibility is that one of them is wrong. The other possibility is that these two estimands are different in important ways, you know, and so, you know, the effect of treating pregnancies within a woman might be different from the effect of treating different women in distinct pregnancies. So you have to think about where that difference might come from. But yeah, I guess that's more typical of the economic approach than the epidemiologic approach, to basically do it all different ways and then compare those and triangulate and see if they're different, having to explain that difference. And it's sort of the idea of the robustness check. Right? The robustness check is sort of like, I'm going to try this several different ways, and if I see anything that doesn't quite fit, I have to be able to explain that. Like if we go back to John Snow mapped out who was getting water from each of the two different companies, and there was an anomaly. There was an address that was getting water from the company that had cholera on the water, and nobody got cholera there. So he went to that address to investigate this anomaly, and it turned out to be a brewery where everybody was drinking beer and nobody was drinking water. So he explained that anomaly, and that he considered that to be sort of the best support of his theory, that when he found an anomaly, he investigated it and resolved it. And that was much better than not examining that anomaly. And this is part of the philosophy of science. Other people, Einstein and others, have also pointed out, like, you know, there are Popper, it's the big refutationist, you know, the opportunity to falsify and then not falsify, you know, you take that opportunity to falsify it and then you survive that falsification test. That's the strongest support for your theory.
Any other questions or comments? Yeah, Richard.
If you're doing multiple sensitivity tests, are you using this? Is this choosing the results you want?
Well, I guess there's a transparency issue there. So if you're an honest economist and you're doing all these specification tests and you're reporting them all and being honest about it, yeah, then it's going to go very well. If you're a dishonest scientist and you're running things 20 different ways and picking the one that has p less than 0.05, then you're obviously going to get a type 1 error. But if you're a dishonest scientist, you're probably doing lots of dishonest things. So you know, in a way, we can't make any progress unless we premise on the inherent honesty of scientists, that they actually want to get the right answer. If you have a big conflict of interest, you're working for industry, or you have a hypothesis that you're really wed to, then there are a lot of different ways. You have a lot of investigated degrees of freedom to mess things up and to get the answer that you want. And, you know, running the model multiple ways is just one of those ways. So, you know, I can't say a lot about that because, you know, the investigator has the data. There are lots of exclusions they can make. And you can see this in practice. You can see people doing the kind of thing, you know, they have a hypothesis they're very wed to. You can see in the literature that they publish the truth of this hypothesis over and over again. And then they get a new opportunity and they go through a lot of backflips and acrobatics to figure out how to get that same right answer again. Like my favorite example of this is the nurses' health study in Harvard, where they're absolutely sure that the thinner you are, the better. Like you're going to live forever if, you know, you have a BMI in single digits, you know. And so they eliminate all the people whose weight changed recently. They eliminate all the people who smoke, because of course smoking lowers your life expectancy, but it also makes you thinner. They eliminate, you know, all the people who did this and the other thing, and they get down to a data set that's only, you know, 5% of the original data set. And sure enough, it's a linear dose response. For the thinner you are, the better you are. So I think that is, you know, transparently biased in the sense that they get rid of everybody who doesn't give them the answer that they want until they have a small enough data set where they can get the dose response that corresponds to their favorite theory. But you can see that happening. Like you can see all those exclusions, and the data set's public, so you can go back and check it yourself and see what would happen if you didn't make those exclusions. Like the fact that we have a community of scientists who, assuming we have sharing of data and sharing of code, the fact that we can check each other's work puts some kind of limits on how far you can abuse that system.
How does this affect the hierarchy of evidence? I'm thinking of, for example, the Cochrane collaboration, who will start with a very large number of studies and gradually narrow it down to about 3 or 4 that meet their very, very strict criteria for high quality evidence, rejecting all the rest. And you make the point about John Snow as a card-carrying member of the John Snow Society. he actually triangulated it because it was not only the brewery who actually had their own water, but they took their own water to make the beer. So that was doubly safe. But there was also the widow of Hampstead, many miles away, who liked the water from what turned out to be the Canada pump so much that she sent her coachman down to collect water, and she became sick, and she and her daughter died. So you have that those two outliers. But if you take the cognitive approach, you've lost all your outliers. So you've lost all the cross text.
Yeah, I'm troubled by that as well, especially because I think the judgment of high quality versus low quality study is very subjective. So I can believe that there are some studies that have more information and less information. But when you throw away all the studies that have less information, there's a lot of information there that you're throwing away. And so, yes, I'm worried about that kind of an approach. I might rather try to resurrect some information from these weak studies. I think that they're mildly informative, maybe, not as informative, but mildly informative, and they should enter into some kind of a weighted analysis in some way. But that does raise another point, which is that I talked about this bias variance trade-off and the way that you want to make a decision based on your study. Like in the Lancet paper here, they wanted to make a decision about whether ART was safe or not. And the newspapers reported, okay, ART is safe, so this is our decision based on this one study. And then the width of that confidence interval becomes very consequential. But suppose these authors were not going to publish or not publicize their work so widely, but they were just conducting their study, and then everybody else was conducting their own studies, and everybody at the end of the day was going to contribute their individual studies to a meta-analysis. In that case, then the width of the confidence interval is not so consequential because you're getting the precision from the pooling of all these other different studies. So they would not be so concerned about taking, that in that case, the calculation becomes a little bit different. You don't really want the more precise but less valid point. You want the more valid point, even if it's less precise, because you're going to get your precision by pooling it with all the other studies. And so that's another fundamental challenge, because I think that's probably a better recipe, a social recipe for the conduct of science, is that we all do our studies and then we dump them into a big Cochrane collaboration, and this pools the information and comes up with a summary. And that's the policy relevant summary. But instead, everybody goes to their press office and issues a press release and says, from my study, I learned that ART is good for you, or I learned that ART is bad for you. And that's the wrong way to do it, because of course you have much less information from your one study and this kind of type 1 versus type 2 error problem. So that has to do with the culture of publicity that plagues both epidemiology and economics, that the university press office wants to put everything in